Really excited to be part of this session. In some ways, I think that what I'm going to talk about today is it's really excited to be part of this session because this is really the state of the art in terms of interfacial characterization in a lot of different ways. This is going to be a bit more of an overview, but as promised, towards the end, I'm going to show some of the results that came out of Kavya's thesis related to fiber breakage during this dispersion process. Just a very quick, and the early part of the talk is going to focus sort of on motivation and the objectives of why we pursue these studies. The first figure that's shown up here, this is a great figure that Professor Shah and Consta Gudos presented in Concrete International a few years ago that showed that the real power of carbon nanomaterials is to decouple us from the classic relationship between compressive strength and elastic modulus, where our elastic modulus only increases by the square root of our compressive strength. So in order, and obviously higher compressive strength has big implications on cost, big implications on sustainability. So the ability to conduct that decoupling has a real potential to transform the industry. So that's a prior result that is very exciting. There's also another result down here showing just another example of a property that is significantly improved by nanomodification with carbon nanofibers. So a reduction in autogenous shrinkage. And there's many more as well, but this is just a couple of them for you to understand why we're pursuing this work. And I think there's actually, I was a skeptic about carbon nanomaterials early on, and I've sort of come around to see it, but I do think there's a lot of questions, open questions that remain, that I want to address some of them today. I'm not going to address all of them. And I'm going to address some of them through some prior results that we've seen before. These first two questions, an explanation of property improvements that are out of proportion to the dose. So Maria's previous talk talked about 0.3% CNTs with huge improvements in elastic modulus. The results I'm going to show here are at even smaller doses, 0.1% CNT, where we're seeing not as dramatic increases in elastic modulus, but still out of proportion to that dosage. All right? And then the second question, this is one that when people think of carbon nanotubes and carbon nanofibers, they're one-dimensional materials, so people naturally start to think about fiber reinforcement, I think. And that's a question that I think we should address is, are these materials really acting like what we think of when we think of fiber reinforcement? So I've got a couple of results that hopefully will illuminate that. I'll actually touch on that. This first set of results sort of touches on both of those questions. But if we think about a fiber reinforcement effect, if we reinforce, when we add fibers, we're reinforcing the cement paste. So we can see an improvement in some measurable properties in the cement paste. When we take that same cement paste and test on mortar or concrete, we should expect a dilution of the property effects. However, with these carbon nanomaterials, we are seeing a increase in the properties. So, for example, a Young's modulus improvement that was only 21% in cement paste, we see larger increases in concrete and mortar. And that is in spite of the fact that the volume fraction is going down because the carbon nanomaterials are diluted relative to the other materials. So this is sort of in contrast to thinking of this in terms of fiber reinforcement. The other way that we've been looking at this, and this feeds directly back to the subject matter of this session, interfacial behavior. If we do SEM EDS on the interface between aggregate and cement paste, we'd expect to see a transition zone. And if we identify the transition zone as typically 10 to 20 microns, which is what we usually associate with the interfacial transition zone, and we make measurements within that transition zone along these lines, which are radiating perpendicularly from the surface of the aggregate, we can measure the calcium to silicon ratio and see that we have a tendency towards more CSH in that interfacial region when we're adding carbon nanofibers, and we also see an increase in the elastic modulus through QNM in that interfacial region through the use of carbon nanomaterials. So both of these things allow us to sort of address these first two questions we're not just, this is not just a physical change. Adding these materials is not just a physical or mechanical change, we're chemically changing what's going on inside the materials. And the next two questions are things that Kavya specifically addressed in her thesis. Those are the things that I want to cover today. And the first one is, although aqueous dispersions are successful, can they be optimized for yield or performance? And sort of the first step in answering that question is to understand what's in our dispersions a little bit more clearly. We have a lot of experience with a lot of different research groups around the country and around the world where these aqueous dispersions produce good results, produce successful results, but we don't have a full understanding of what's in those aqueous solutions. And then secondly, scaling the dispersions for industrial use. Right now, a lot of us are working on the laboratory scale, and so there's some open questions about how we can scale these to industrial use. Understanding these, and again, I'm talking to people who are maybe a little bit less familiar with the carbon, a little bit less familiar with nanomaterials than some of the other speakers in this session, but a real important thing to keep in mind is these are fundamentally different materials, especially in terms of their specific surface. Like we're 2 orders of magnitude more specific surface compared to silica fume, and over 3 orders of magnitude higher than most of the other components of what's in there. So this underscores the challenge of dispersion, which is what Maria was speaking about in the previous talk. The other thing to keep in mind is that this aspect ratio. So these CNTs and CNFs that we work with, typically the diameters are measured in tens to hundreds of nanometers, and the lengths are in tens of micrometers. So we have an aspect ratio in the ballpark of 1,000. I think you were dealing with materials in the prior talk with an aspect ratio of 900. So keep that in mind, because that's going to come back. And again, I think a lot of us are familiar with this process, but maybe not everyone in the room. But the dispersion process that a lot of us have been talking about here is a mixture of water and the as-provided materials, carbon nanotubes or carbon nanofibers. You mix them together along with a surfactant of some sort. Superplasticizer is one that seems to work. Polycarboxylate superplasticizer is the one that seems to work pretty well. And then you apply energy. Mechanical energy in some way, ultrasonication is the laboratory scale that we've been doing so far. Then that produces a CNT suspension. You then do some sort of dispersion quality assurance, which can be very simple to very complicated. But the idea is that this CNT suspension becomes the mixing water for your mix. All right. Here's the simplest type of dispersion quality assurance you can do. You can look at it. And if you see, this is not a way to accept a dispersion. This is, however, a way to reject one. If we see a dispersion that looks like this, where we're very dramatic, see a very obvious settlement of material, that's very clearly not well dispersed. This one, where it kind of looks like a black water, is a candidate to be well dispersed, but you can't necessarily say that it's for sure well dispersed. Just for the visual inspection. Professor Conce talked about DLS as a good way to assess the dispersion quality analytically. She also alluded to UV-Viz as a good way to establish how well dispersed our materials are. So I'm going to talk about that very briefly, but then we can use the work that Kavya did in her thesis was to isolate individual fibers in the suspensions and image them such that we can evaluate their sizes. So UV-Viz, very quickly, again, we're looking at dispersion of ultraviolet and visible light. Pointer here. And this is the spectrum of dispersion over increasing time of sonication. And this plot to the right is a plot of, I believe it's the value at 400 nanometers, like how well dispersed it is. And basically, the higher the spectrum is in this graph, the more nanomaterial you'll have in suspension. So you can see that we rapidly increase the amount of suspension in the first hour or two of sonication, and then it does increase beyond that, but it's definitely a much more attenuated rate at which that increases. Another study that Kavya did was to look at the stability of these suspensions. So after you sonicate with superplasticizer, there's a question about whether the carbon nanomaterials will re-agglomerate. And what we found is that they do settle. So this is a plot of UV-Viz over time as a specimen sits. So it will settle over time. However, if you agitate it, and not even sonication, just literally shaking it, you can bring it back to the dispersion characteristics that it had before. So that's just a very quick intro to UV-Viz. The new thing that I wanted to talk about that Kavya worked on is drop test characterization. So what she wanted to do was image materials in the suspension. So her first crack at it was to sonicate, create one of these suspensions, and then take a drop of that suspension, put it on a silica substrate, dry it, and then image what was remained. What may be obvious to you, but wasn't obvious to us at the time, was that was going to give you gibberish. When you do something like that, you get a huge amount of carbon nanomaterials that are very difficult to discern what's going on in that block. So you have basically thousands of individual fibers on top of each other there. So if you wanted to do a size characterization or anything like that, not possible with this method. But through our collaborators in material science, we worked on another method that they had developed where you prepare the substrate such that the dispersed CNT that have the superplasticizers adhered to their surface, we create a surface such that this Aptest polymer adheres to the surface, and then that polymer grabs onto the CNT. And then the idea is you do that, and that'll create one layer of CNT, and then you wash off everything else, and then you image what remains. So this allows us to create a monolayer of dispersed CNT on the substrate, which we then can image. Once we do that, either SEM or AFM. We started with AFM, and we quickly realized that SEM can give us the same particle size distribution with a lot less time and money. So SEM is what we went with. First question: are we seeing an aspect ratio of 1,000 in this image? For sure not. We have aspect ratios much less than 1,000. And that is what we wanted to measure. So what we did is Kavya developed a image processing technique where she is able to take a raw image, process it, and calculate the length of the particles that are in there. And this is an example of a particle length distribution for this image to the right here. And I don't know exactly how long this specimen was sonicated for, but the mean length of the particles in this suspension is around 1 micron. And so what she did is she pulled out samples as a suspension was being sonicated, pulled out samples every hour or so, and then did that particle size distribution. And I'm sorry we don't have a summary of the results here, but I can read them off to you if you can't read them. After about 1 hour, we had about 3.5 microns mean length, and that dropped to 1.6 microns at 2 hours, 1 micron, I think that's around 5 hours, and then it drops under 1 micron at 8 or 9 hours of sonication. So you can see that to answer the question from the previous talk, for sure we are breaking the fibers, at least the fibers that we're able to image. So there is an argument one could make is, with this method, are we only grabbing smaller particles? That's certainly something to consider. But anyway, among the ones that we are imaging, they're certainly on average much smaller than what we would expect based on the information given from the supplier. And they are also, the size is getting smaller as we sonicate for longer and longer periods of time. All right, last thing I want to talk to you about today is scaling up. We started to investigate high-speed shear mixing as a way to disperse materials. So at least our setup in our lab, we're limited to about 350 milliliters of sonication at a time. There is, with our partners in material science, there's a high-speed shear mixing setup that allows you to mix up to 3 liters at a time. And so Kavya set out to do the same set of characterization methods to see if we're getting the same type of dispersion from high-speed shear mixing as we are from sonication. And the result of that, these are some of the results from that. This is, again, an example. This is an example from the from the sample that was about, I think, 4 hours of sonication. She saw a similar progression where we're losing length in the particles as it progresses. And lastly, I wanted to share the results on mechanical testing. This is just a very simple round of testing. It's not as thorough as what we had done previously or what Professor Constance's group is doing, but it does show that we are, compared to control specimens, this is with 3-point bending fracture specimens, we do still have an increase in elastic modulus. So we do think that this shear mixing, high-speed shear mixing, does perhaps point to the direction of what could be an industrial application for these materials in the future. In conclusion, I have gotten to the point now where I really do believe this, that the carbon nanofibers and carbon nanotubes are acting more as a nucleation or seeding agent, more than they are acting as a fiber. And we're seeing significant fiber breakage for these well-dispersed aqueous solutions. And we have promising results in terms of things that we would need to have in order for these materials to be used in the field. Stable dispersions that do have the potential to be dispersed in large volumes. The last question I don't have an answer for, the energy and cost associated with these materials beyond the scope of what we're going to talk about here today. But those are things that need to be talked about.